I'm Renita Malhotra Hora, Director of Marketing and Communications at SRI International, and you're watching The Dish. You use statistical models based on physics.
Yes.
Is that right?
Yes.
To identify viruses and ribosomes?
So for my research background, as you mentioned, I'm really focused on the idea of using physics-based statistical models to extract information out of large collection of image data that are collected by this cryo-electron microscopy technique. So overall, our goal is to understand the three-dimensional structure information and temporal dynamics information of biological particles like viruses and ribosomes based on large 2D collection of projection images.
So when you talk about temporal dynamics, define what that means for me.
So the cryo-electron microscopy technology, one of its core key advantages is really like that compared to the earlier cryo X-ray crystallography methods. It would actually capture the particles at a random stage of its natural motion. So this allows us to extract information about the motion of the particles. So that's what I'm referring to as the dynamics of particle, like how would the various particles behave when it's in its natural motion, because they're not static, they're kind of vibrating. So what is the way that they tend to vibrate? Like, for example, one of immunoglobulin, we're looking at this kind of have a Y-shaped structure. Then whether these two arms of the Y-shape, are they mostly like moving in synchrony, or are they moving mostly 180 degrees out of phase? So that would be one interesting property that we can analysis based on the dynamical information.
Cryo-electron microscopy. Can you explain what this is?
Yeah. Cryo-electron microscopy, we call it cryo-EM. It is the technology that is awarded by the Nobel Prize in Chemistry in year 2017. So essentially, it's the imaging techniques that you apply transmission electron microscopy to the particles that are flash frozen in liquid nitrogen. This would allow...
Is that what the cryo is?
Yes, cryo, I think, is referring to cold, so flash frozen in liquid nitrogen. So then, in compare with other imaging techniques that would, for example, X-ray crystallography, it would require your samples to first form a crystallized structure. But this cryo-EM, so it would actually would not have the requirements, and it would actually capture the image instead of in a static crystallized structure in a random stage of its natural motion. So that's the key property we're interested in because it allows us to extract dynamical information.
Beyond the study of viruses, ribosomes, nanoparticles, such as those, are there other interdisciplinary applications of this?
Yeah, so one of the ideas is that we kind of imagine the statistical framework we propose as a very general image understanding framework. We call it Various Hollywood because we're understanding it as a complicated reconstruction where you extract three-dimensional and first-dimensional information out of large collection of 2D data. So the ideal data one would like to observe some nanoparticles in its natural motion would be a movie of the particles in 3D. But actually what you can acquire through these imaging techniques is like you randomly withdraw several frames out of the movie and you shuffle the frames. So you lost the temporal orders of the frames. So our goal from statistical point of view is really trying to reconstruct this movie and bring the particle back to life in a way that makes most of the sense in terms of probability. So we demonstrate that we can actually apply the similar techniques in various interdisciplinary application domains. For example, we are working on one of the first efforts to apply cryo-electron microscopy technique in the domain of material science, where instead of organic nanoparticles like viruses and ribosomes, we're interested in identifying the structure of those synthetic, inorganic silica particles that are developed by our collaborators.
So definitely physics, biology, physics, chemistry with the material science. Yes. Is that right? But here you're doing something a little bit different right now.
Yes.
Right?
Yes.
You're working on the applications of physics to artificial intelligence.
Yes, so more recently, I kind of been mostly involved in developing approaches of image understanding with a different flavor. So, which is those deep learning-based approaches that is featured by its capability of capturing a data set empirically. For example, I have been working on more of a classic computer vision problems using tools, exploring tools like generative models, unsupervised and self-supervised representation learnings, and the meta learning. So one of the example of my current work is the problem that we are trying to tackle the challenge of label scarcity. It's kind of well known that a lot of empirical success of deep learning really relies on a large collection of training data with adequate label. So in general, we're interested in the idea of learning with less label. So in particular, we are developing trying to incorporating unsupervised and semi-supervised approach to the problem of few-shot learning. So few-shot learning is this problem that you would like to learn a model that is able to transfer to novel classes. So intuitively, it's like a kid can actually recognize apple after only seeing it once. We want the deep learning models to have the same capabilities so that they can transfer and generalize well.
So the physics aspect of this, can you explain that to me? What is it? How does that work?
So actually, because I kind of have this experience involving two different flavors of imaging understanding, so I'm really interested in the idea of kind of incorporating them as a complement of each other. Because if you look at the traditional physics-based approach, which is completely based on analytical models, it had the advantage that it can incorporate all the physical priors you know about the imaging process, about data collection, and it will allow you to incorporate parametric uncertainty. Let's say if you want to estimate a parameter of specific physical meanings in the process. But such traditional methods is often challenged by the so-called curse of dimensionality. So
the curse
of dimensionality, especially in a very complicated real-world circumstances, it may be very challenging to describe a very accurate model with just a few parameters. So dimensionality referring to the numbers of parameters you need to describe the real-world problems.
Why is it so important, in your opinion, to integrate physics into this deep learning process?
Because I feel like currently a lot of deep learning success, they are based on those, like, for example, ImageNet data that is curated and specifically designed for research purpose. So we need to think about more fundamental approaches, for example, to incorporating physics to provide better interpretations of the current deep learning success. That's why I feel it's very exciting and interesting area to explore.
Thank you, Yunye. That was very informative.